Thank you so much, Allison. So thank you all for being here. I'm Tal Garfinkel. I'm a research scientist at UC San Diego. Did my PhD at Stanford. Prior to that, I spent about, or sort of during, before, after. Actually, I guess during and after. I spent about a decade at VMware from the pretty early days when it was just a couple hundred people till it was about 26,000 people. So my kind of formative years were spent seeing the impact that virtualization had on the industry from the point at which it was kind of like laughable that everything would be running in a virtual machine and VMs slowed things down by like 30% to the point where it was a given that, of course, you're going to be running in a VM. So today I'm going to be talking about a few different things, and I kind of try to break this into two parts. First, I'm going to talk about like what is WebAssembly kind of as an isolation technology, and how is it being used. And what I was hoping for here is that even if you're kind of not into the sort of gory details of Wasm, or you haven't used it before, you'll kind of come away with some idea, oh, this is where Wasm might be useful in a project for me. For a security project, for some extensibility piece, for some serverless piece, someplace where like, oh, okay, this fits, right? Because Wasm is kind of this distinct point in the design space. It's not containers, it's not VMs, it's this other thing that you can use. The second part, I'm going to talk about the research that I've been working on recently, and this is kind of how do we push beyond Wasm's limitations, right? Wasm is kind of doing something fundamentally unnatural, right? It's where we're taking software and we're using it to overcome the limitations of hardware. And again, this is kind of close to my heart because of my background in virtualization. So if you kind of know the history of virtual machines, VMware, when it started out, right, was virtualizing the x86, which was something you could not do, right? The x86 as an architecture is not virtualizable. So instead, what VMware did was use a combination of low-level hardware features and binary translation to make the x86 virtualizable. And this is how we were able to get virtual machines. And for the first 5 years more, right, there was no support from the hardware, and this was the only way to do it. And eventually, hardware caught up, and we got to this world where writing a virtual machine monitor is a project for a graduate student. Anyway, so let's get into it. I think I see this kind of nice parallel between Wasm, where again we're using the compiler and software to overcome the limitations of hardware. And yeah, so let's get into it. So isolation is fundamental to how we organize systems. We have kind of two different technologies to do this. We have hardware-based isolation, right, which relies on the page tables and protection rings, and this is what processes, VMs, and containers are built on, right? We're all familiar with this. It's language independent, bare metal speed. Unfortunately, it's designed to be relatively coarse-grained, right? Communication between different protection domains is quite slow. Starting one of these things up is quite slow, and it has a relatively large resource footprint, right? Fundamentally, hardware-based isolation today is not about doing fine-grained things. The other place where we see isolation, we kind of take it for granted, I think often is within programming languages, right? So this could be modules, functions, or in programming languages like Erlang and OTP, right? Processes, we have kind of soft processes, right? So these are language dependent, right? And they impose runtime overheads, but they can be very, very fine-grained, right? We can start and stop these things in nanoseconds. They have very small footprint, so and they really kind of match how we think about things. WebAssembly is based on a technology called software-based fault isolation. So software-based fault isolation is an idea that goes back to the 90s. This was a few years before I got to Cal as an undergrad. And folks this is kind of in the middle of, I'll say middle of the time of, or the kind of heyday of extensible operating systems. So people were thinking about microkernels. People were thinking about writing kernels in safe languages, right? There was this, like, how do we get more flexibility into our systems? And one of the ideas that came out of this was, well, instead of using hardware to enforce protection, what if we use the compiler? So SFI, it sort of exists in this liminal space, right? It is relatively language neutral because it has this model of memory that looks very much like the underlying machine, but it lets us get these nice properties that we usually get from software-based isolation, right? Orders and orders of magnitude faster context switches than we're going to get from VMs or containers. Orders of magnitude faster startup times, small resource footprints, massive scalability, right? And this is what makes companies like Cloudflare and Fastly able to do what they do with this kind of like hyperscaling that they do with edge-based serverless. So, so what is WebAssembly? So, right, so it's a platform-independent IR that you can AOT or JIT, and right, so it isolates components within a single address space. Generally like within a single OS process. And sort of, how is this possible, right? Well, it takes a lot of work. So it started out as a web standard, right? You have to get all these various languages to target this new VM. You have to grow the ecosystem of tools to support it, and then build a community around it. And this is kind of where we are today, right? We're about, let's see, 6 years into this journey from when this first emerged, and all the major browsers supported it. And now we're, it's seeing adoption on the edge, and a lot of folks are starting to use it in different applications that I'm going to talk about next. Right, so how is Wasm being used? So the first example I'm going to talk about, which is not the biggest example, but it's the one that's close to my heart, because it's the stuff that we've done, is library sandboxing. Right, so Firefox uses WebAssembly to isolate buggy libraries. And this has been a close to, I think, like 5-year project now, from talking to our friends at Mozilla and recognizing there's this problem, right? When you're using your browser, when you're going to a website, your browser is rendering all sorts of different content, right? Media, XML, audio, right? Like all sorts of different formats. There's dozens of libraries to do this. It uses these libraries for spell checking, right? Tons and tons of third-party code, right? Dependencies. And these are all written in C. And when any one of these has a vulnerability, right, that can compromise your renderer. So for example, let's say I send you an image file. That particular library has a buffer overflow in it, right? I pop that library. Now I have control of your renderer. Now I have control of that application. So I have control of your email client. I may also have control of like everything else in that site, because we do have site isolation in browsers. So maybe I've got mail.google.com, but maybe I also have pay.google.com for you. Maybe I also have cloud.google.com for you. Right? So it's a very, very serious class of attacks. And so what we found is that it's actually not easy, right? We kind of had to build some tooling and infrastructure to enable this, but that with the appropriate tools, we could start sandboxing these libraries. And so this has been shipping in Firefox since 2020. So today, if you're using Firefox, right, a bunch of those libraries are actually sandboxed. And right, this isn't particular to, oh, sorry. I've got the performance overhead is low slide. That's mandatory. And this is not particular to Firefox, right? Like every application out there depends on C and C++ libraries. Right, this is where most of your bugs live, is in native code, right? A majority of our bugs are in these C and C++ libraries. And most of the stuff languages that you use rely on these libraries, right? So you may be like, oh, I don't have to care about this. I'm writing in Rust or Java or Python, like whatever language you depend on, you probably have a large number of dependencies that are actually just C libraries that have been wrapped by these languages. And so what we're doing now, and as part of our research, is working on how do we get this out of, we built these tools for C++, for Firefox, but how do we get this out there and actually into the ecosystem, right? How do we build this as something that you can opt into, like when you pull a crate on Cargo, or when you pull an MPO on Ruby, to say, okay, or sorry, on Node, to say, okay, I want to opt into the sandbox version of this library. And if this is something that's interesting to you, that could improve your security profile, I'd love to talk. So again, there's lots of other examples of how you can use Wasm. A big one of these is serverless, right? So today, again, the edge platforms use this for hyperscaling. This allows them, right? So every time these guys get a packet, they spin up a new instance, right? And because they can get low context switch overheads, right? They can run many of these things concurrently without paying the context switch tax. They can start these up in microseconds. And they can use orders of magnitude less memory than they might end up if they're using a VM. Again, plugins and extensibility, and this is a huge area. So if you're using a service mesh, Istio, like Envoy and Istio, Shopify has used this for running user code server side, stored procedures, that sort of way of using this, and Kafka. Right? There's also sorts of places where you're like, I would like some safe extensibility. I want to put some code close to my data path. And Wasm is a great tool for that. Another place that Wasm is really catching on is in the IoT space. Because right, you have this whole diversity of different devices, and you have your developers that are writing your application code, and you don't want them to have to worry about all the fussy details of the different compilers, different devices. And so Wasm's platform independence is being used as this layer to kind of shield people who are writing the application logic from the particulars of the different IoT devices. And this, I think this is going to be very big. I think as we see more and more intelligence embedded in different devices, this model where whether it's Microsoft or Amazon or someone else is dealing with software updates and distribution and all these things for you, and you just build your business logic, or your, I guess it's business logic in Wasm. I think that this is going to be sort of a really important model for using Wasm. So this sounds great. You've got this really lightweight isolation technology. But how does this compare to running on bare metal? And the reality today is, right, there's a lot of limitations. One of these is performance overheads. Right, another of these is scaling. And again, out the gate, Wasm is still better at scaling than kind of your traditional hardware solutions, but it has some limitations as well that I talk about. Spectre safety is a big deal. Just out of curiosity, who knows why the little ghost is carrying a stick? It's a branch. Yeah. 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 I know, I love it. And finally, compatibility is an issue, right? Like, essentially, Wasm is para-virtualization, right? Like back in the day before we had virtualization hardware, it was like, let's change the operating system, right? This is what Wasm is doing, but it's like, let's change the compiler to output this new IR. And some of that is like we're dealing with, and some of that's fundamental. Sorry, so just quick review before I get into this. Who all remembers undergrad operating system? Just does everyone remember page tables and TLBs? Yes, OK. So, right, we've got we go looking for memory. So page tables are incredibly powerful. They're like this amazing thing. You can use them for compression. You can use them for live migration. You can use them for overcommit, right? It's a really, really powerful abstraction because, as we know in computer science, we can solve any problem with a level of indirection. And this is what page tables are. The problem is that our TLB is a bottleneck. It is a bottleneck in terms of like how many things we can shove through there, because if we have too much concurrency, it becomes a point of contention. And if we want to modify our TLB quickly and dynamically, things get weird. Something you probably don't see every day, but again, you probably read about in undergrad, or who all remembers segmentation in x86-32? Yes, OK, got a few takers, cool. I do. So the kind of other choice we generally have over architecting systems, right, is segmentation. There are other forms of memory management out there, but this is kind of a big candidate. And so segmentation works differently, right? It is one of the earliest forms of memory management. And here we have this notion of base and bounds. And it doesn't have the issues of the TLB, right? It has its own limitations. Right, but our model is when we do an address lookup, we do it like usually relative to the start of a segment, and the segment has permissions and whatnot. So it's kind of an alternative scheme. Why am I talking about this? A lot of the limitations that VMs and containers have that are fundamental have to do with the fact they are dependent on page tables. This limits scale and it limits dynamism. Right? If you want to create these things, if you want to destroy them, if you want to resize them, you will shoot down your TLB. This is expensive. Again, if you end up with many of these things, you'll end up contending for your TLB. I review papers, and sometimes I get these papers, and they're like, oh, like we have like address space identifiers, and so we can tag things in our TLB, and like this is how many of them there are. And I'm like, the number you're telling me is actually much larger than your TLB physically is. So you are going to be fleshing your TLB. So again, TLBs are incredibly powerful, but they do have these kind of inherent limitations. The other limitation are context switches, right? And part of this is protection ring crossings, but protection ring crossings are actually not that bad, right? Maybe they're in the tens of nanoseconds. But the scheduler is pretty expensive. So you have to buy, if you have to buy into the OS scheduler, that's going to cost you. Doing a heavy rate save and restore is going to cost you, right? There's all these things that take us like well beyond the realm of, there's also going to be cache pollution, right? There's all these futzy things that if you have to go back and forth between the operating system, when you want to switch between partition domains, it's going to get way more expensive than if you can just basically do a function call, which is what's happening in something like Wasm. When you I make these comparisons to Lambda sometimes. You can spin up a Wasm instance in a couple microseconds, whatever. And with a Lambda, you're talking like 100 milliseconds. But really, right? Then there's the OS overhead, OS overheads. There's language runtime overheads. Whatever funny thing they're doing in their virtualization layer. Recently, Microsoft has their kind of like Hyperlight, their very lightweight hypervisor that they're going to use to run Wasm in. And their startup times are still like, they're saying like 100 microsecond scale, which is still a couple orders of magnitude off of what we can get with just kind of like straight up Wasm. So what is the alternative? And the alternative, again, is, software-based fault isolation. And to me, software-based fault isolation is poor man's segmentation. Where we don't have hardware segmentation, so we're going to do this in software. How do you do this in software? Two ways, right? The simplest way that you could think of to do this is just add bounds checks to every load and store. The problem with this is that this is expensive. Right? You're adding iCache pressure, you're adding the cost of executing those checks, you're chewing up GPR, general purpose registers to keep around those bounds. All right, so you're easily looking at a 40 to 100% slowdown on real benchmarks. And of course, you're not Spectre safe. So that's mostly not what people do. If you look at a production Wasm implementation, if you look at what's happening in your browser, if you look what's happening server side, what people are doing is they break the address space up into guard regions and address spaces, right? So in Wasm, I'm doing 32-bit memories and a 64-bit address space. So I can break this up into these 8 gig chunks. The first 4 gigs is my address space. The second 4 gigs is a guard region. And when I'm doing addressing in Wasm, so if I'm doing 32-bit unsigned loads, I take that, I add that to the beginning of my memory base address, and now I've got a 33-bit value, 8 gigs, right? So it's either going to land in my address space or it's going to land in my guard region. So what did this do for me? So this lets me get rid of my bounds checks. I still have to do that base addition, right? So I'm still adding an instruction to every loader store. Every loader store is going to be base addition and then the actual loader store. But it helps a lot, right? It helps getting us down to maybe 15, 20% range. So it's a big win. This also has limitations that it brings, though, unfortunately. Some of these are, I'm still involved with the MMU, right? Have not escaped, right? First, setting up and tearing down memory. There are other limitations I get, right? One of these is the guard regions, right? They scale poorly, right? So on x86 in user space, I've got 2 to the 47 address space. Right, each of these 8 gig regions is 2 to the 33. I do my math. I've got 2 to the 14, or about 16,000 instances that I can put in here. I can arrange things a little more cleverly and get about 20,000 instances. So this sounds great. The problem is that when I'm using this in a serverless context, again, right, I'm spinning up one of these, right, in every time I get a number request. And each of them is often running under a millisecond, right? Because I don't have all those funny overheads with Lambda anymore. It's just running my code. So filling up an address space is pretty easy. So I fill up one process address space, so I could start another process, another. But then I've got context switch overheads. Then I've got IPC overheads when I talk to them. If I want to chain functions, I'm getting back into the space that I was trying to get away from. The other thing is the component model. right? So a really, really great thing about WebAssembly is, right, the component model. It's this new thing where instead of running your application in one address space, you'll be running your application in multiple address spaces. So you can have components. You can have your dependencies broken into separate isolated things. Could be one library, could be multiple libraries. But we're talking about potentially like an order of magnitude or more increase in the number of address spaces per application, right? So we need to do something about the scaling limit. The other problem with this guard region scheme, we can't use it with 64-bit memories, right? We're back to conditional checks. And we can't use it with older processors, right? We can only play it under these particular conditions. And finally, these tricks that we're playing still have overheads. So the final limitation, again, is compatibility. So this is a big one. This is a big one today if you're going to be using Wasm for real projects. And I can talk about like what you can do now, what you're going to be able to do in a year, what you're going to be able to do in 2 years, right? Because you're presenting this interface to programming languages, to compilers for them to target. So you need to provide a rich enough interface to get them what they need, and you also need to provide a rich enough interface that they can exploit all the functionality in the hardware. Some of this is getting better standards. Some of this is just fundamental to like how Wasm works that we're not going to overcome. For example, like I don't think dynamic code generation is anywhere in the near future. You're never going to be able to kind of do direct system calls, although a lot of this stuff can be supported by WASI. And you're never going to get your platform-specific assembly to magically run in Wasm. Although we have some tricks for dealing with intrinsics that I'd be happy to talk about. So 2 things. How do we do better with current hardware? And then how can we extend hardware to overcome these limitations? And by extend hardware to overcome these limitations, I mean the limitations that Wasm has, but like all the way to how do we get these properties that Wasm has, right? Super fast startup, teardown, communication, like all this goodness, without even having to get into Wasm, right? Just for native binaries for whatever code you run. So first, optimizations. So I have 2 things that I'm going to talk about that we're doing today, kind of using hardware in dirty ways to make things go faster. First one is an optimization called Segue. It's super simple, and it takes about 25% of Wasm's total tax away. The second one is one called Color Guard, and this addresses that scalability problem I mentioned and lets you go from the 20K instance max to about $250,000. So back to segmentation. I just love this topic. I keep on coming back to it. Right, so segmentation was largely removed when we moved to x86-64. Right, Intel was off doing Itanium, and AMD was like, never mind, here's the new standard. And as part of that, they dropped segmentation. I'm sure it simplifies some things at the microarchitectural level. There was good reasons for doing this. And what we were left with was segment relative addressing and 2 segment registers. So right, the rest of our segment registers now don't do anything. You can still use ES, CS, DS, but they just are a bit based to 0. We still use these segment registers, right? If you're using thread level storage, right, it is you're addressing things using segment relative addressing with one of these registers. It's going to be FS in Linux, and I believe it's going to be GS in Windows. As it turns out, we can use this amazing register for other things. I mean, to be honest, you can actually use both of these for other things because in like a Wasm runtime, when you're going to be handing control back to something that's going to be using thread level storage. So the trick is, right, we just take that base addition that we were doing, right, again, like with guard regions, we do a base addition, and then we do a load or store, and we move that heap based into a segment register. And then we just do segment relative addressing. So one instruction became 2. One general purpose register that you were burning, you can just use a segment register you weren't using anyway. And you're getting rid of instruction cache pressure. So you can see our X instruction goes away, frees up an extra register, frees up some extra flexibility for the compiler. As it turns out, we get this big code size reduction, which was kind of a pleasant surprise to us. We get some nice performance reductions on spec. And on specific workloads, we get even bigger jumps that I'll mention a little bit later. So this is actually landed in Whammer, which is Intel's Wasm runtime, or compiler and runtime. just recently, and I flagged that thing, reduces compilation time of JIT and AOT. I have no idea why it makes it faster, but it's like one of these things when people deploy it, it's like, oh, that was great. I didn't even know we were going to get that. So the other trick that we came up with is called color guard. And color guard, sorry, I'm doing time math in my head. Color guard takes advantage of a capability on Intel and AMD processors called memory protection keys. This has been in Intel processors for quite a while and AMD processors since EPYC Milan. So if you're on older AMD hardware, you might be a little sad, but this is relatively widespread. The way that this works is for every page, you associate a 4-bit tag. And we usually think about those tags in terms of colors. And then each core has a tag register. And so if the color in the register matches the color on that page, right, then you're allowed to access it. And if it doesn't match, then you're not allowed to access it. So we have this kind of new, cool protection mechanism. What I can do with this mechanism is I can eliminate that waste that I had. So going back to that picture that we had in our mind, right, we have 4 gig address space and a 4 gig guard region. So let's say we take that 8 gig region and we break it into colors, and we say 500 gigs is going to be red. Then the next 500 megs is going to be red. Next 500 is yellow. Next 500 is blue. Next 500 is green. So we fill that out. So now what we can do, right, is we're using the address spaces of our other VMs as our guard regions. And we want a context switch. We just switch the color of that register. And all of a sudden, we've eliminated that waste. And now, again, we've kind of got this big win, and we can run, order of 12x more instances in the same amount of space. So this is fun. This does not address all the performance limitations. It doesn't even address all the scaling limitations, even with that cool trick, because again, we're restricted to our 15 colors and our 8 gigs. But it's nice. But how do we go further? So after working with this stuff for a few years and kind of beating our head against the limitations of Wasm, we're like, we just really want hardware support. And what do we want from that? We want 3 things. Number 1, we want really simple microarchitecture. And the reason for this is that it's really, really hard to get changes into real processors. You have a very, very limited budget in terms of gates if you're kind of close to the critical path. And so we worked with folks at Intel, and we went back and forth a lot in terms of like, can we have this? And they're like, no. And like, OK, let's figure out how to work around that. Another thing we wanted is minimal OS changes. It is really hard to get Linux to do things. It is really hard to get Windows to do things. For example, MBK is not supported in Windows, and I don't think it's ever going to be. There are lots of like funny, silly things that you like. If you like hang on the kernel mailing list, you're gonna be like, wow, like that is really small. I'm shocked that it is taking this long to get supported. So we're like, oh man, we don't want to be involved with that. The third thing we wanted was this ability to support both Wasm and other sorts of software-based fault isolation against other sorts of compiler-enforced isolation. For example, V8 now has its own custom way of doing this because the V8 JIT is an area that has lots and lots of bugs. And of course, we want to be able to support unmodified native binaries as well. So kind of the whole spectrum of these things. And our solution to this is an extension we call hardware-assisted fault isolation. So HFI is a user space ISA extension, right, that gives us a few key primitives. One, it gives us bases and bounds, right? So this ability to say, OK, like here's a set of data regions, or here's a set of virtual address ranges that I can grant the sandbox access to. Right, so I set up my mapping of virtual address regions. I say, OK, I'm going to enter the sandbox. Once I'm in the sandbox, that's the only memory we can access. I execute my guest code, my sandbox code, and then when it calls exit, it hands control back to a runtime. There's more details, but that's the essential idea. It's dead simple. What HFI provides for us, right, is super fast isolation. Right, those bounds checks are executed in parallel with your TLB lookups, so they add no overhead to native code, which is what you expect with like a page table as well. We get very, very fast statistical interposition, which I'll talk about a little bit later. This gives us some forms of specter safety, which I'll also talk about later. It gives us unlimited scaling, right? It doesn't have any of those constraints that we had before, right? We have a small amount of on-chip state. We context switch that state, and we're done. And we can set up, tear down, and resize sandboxes very, very quickly, right? This is just a change of registers. And finally, of course, this is compatible with existing code. We don't have to get into the whole huge game that we're playing with Wasm. So one challenge. So this sounds like a nice idea. You're like, great. I want to do like upper and lower bounds check. I'm going to implement regions. This is just segmentation. I'm just going to grab two 64-bit comparators. I'm going to do an upper bounds check. I'm going to do a lower bounds check. Amazing. And if you go to an architect and we went to an architect at Intel and we're like, this is what we want to do. They're like, they take away your lollipop and send you home. Right. So, right, we've got a limited gate count. We cannot slow down existing pipeline stages because that'll slow down everything. We can't put complex circuits in there, right? We're right on the data path. So this is going to be described as the Manhattan of chip real estate. So how do we do these checks in a way that requires very, very little silicon? And our answer to this is that you specialize regions to a few different types. And we have two different types of regions. And again, kind of going back to the world of x86 segmentation, remember we used to have segments that apply to all memory accesses and segments that apply where you segment relative addressing. And regions are the same way, right? So we have explicit regions where you do relative addressing. And the nice thing about this is that we can do this with one 32-bit compare, right? Because it's always like one-sided. I'm always just doing, so I've constrained I get all the expressiveness of my x86 move instruction except, right, I'm going to constrain it to say that my index has to be positive. And doing that, right, I can just do a one-sided comparison. And so I can do this with very little hardware. This only works, though, if I'm doing relative addressing. But the other thing I want is to be able to do, just apply this to everything. So how I'm going to do that is I'm going to give up some granularity. Right? With my explicit regions, I can be like, well, I'll have a large region and a small region. With my small regions, where I can address up to 4 gigs at a time, I'm going to have byte granular addressing. And this is really important for doing sandboxing. Right? When we sandbox libraries in Firefox, we do not want to change them. Somebody else maintains that code. We want to be able to say, this is a data structure. Here is where it lives in memory. I'm going to map that into my sandbox without changing code. For that, I have to have byte granular addressing. For larger things, so again, remember, with Wasm, I'm doing things relative to the base of linear memory. And actually, I want this because with Wasm, I can have many linear memories. And so I'm going to use my region relative addressing for that. But there, again, I only need to grow it in 64K chunks because, right, I'm growing my heap. And then with implicit regions, I can use this for code. I can use this for static data. I use this as for stack, right? It's because I'm using masking, right? I have to be power of 2 aligned and sized. But often, I can deal with that extra slop. And what I get for that is very, very cheap implementation. So another thing that I really wanted early on with this was system call interposition. And the reason for this, well, it's just that it makes the things a lot simpler. I've written probably 6 different systems that do system call interposition. I've done library interposition. I've written a new process tracing mechanism for Linux. I've used Linux ptrace. And on all of those experiences were terrible. Right? Modifying the kernel is terrible. Using the existing thing is really kind of expensive and slow. And library interposition is just really fragile. Right, when you can change the processor, you can do something really, really simple. You can either just change microcode or implement this with conditional logic. You can just say, every time I see a privileged instruction, syscall, sysenter, and data, whatever, right, turn that into a jump. Just return control back to my runtime. And it's just, yeah, it's just, I really like it. It just makes me really happy, irrationally so. Or maybe irrationally so, I've got some scars. Anyway, another thing that we get from this is really nice is that we get specter-safe bounds checks, right? When we're doing bounds checks in software, our processor does not know about this. It will happily speculate them, past them. Now that we're doing things in hardware, we can architect this so, right, whether a memory access is speculative or non-speculative, a bounds check will get enforced. So that means we're never going to speculatively access something outside the bounds of our sandbox, right? So we've got our sandbox memory region, and even if like I mistrain the processor, right, like it will not speculate beyond the bounds that are being enforced by HFI. This does not solve all of Spectre, right? Spectre is fundamentally there is no easy solution to Spectre, right? The problem with Spectre is that it relies on, right, branch prediction and out of order execution is like deeply ingrained in how we build processors, and this relies on prediction structures, right? The PHD, the RSB, the BTB, things that like, you know, is this branch going to execute? When is this branch going to execute, right? And branch prediction is key to how you go fast, right? Like you need to kind of keep on going, keep on fetching into your pipeline, and what we can't just go and flush those structures, so like we can't solve this, and nobody else seems to have a great solution either. Okay, so we've got these primitives. They work for Wasm and other SFI workloads and for native binaries, and we just use them differently in those different scenarios. But two different use cases, sort of two different usage models, but essentially the same primitives. So how does it work in terms of performance? Well, in simulation and in emulation, and in emulation we validate with our simulation, we get a huge speed up if over doing bounce checks, which is great for 64-bit memories. Over guard regions, we get a little bit of a speed up, which is nice, but we also get all these nice properties in terms of scaling, Spectre resistance, large or small address spaces. And on some workloads, right, that, you know, reducing register pressure and iCache pressure and, you know, all those sort of good things I was talking about before, get some really big wins, right? Like here with image rendering in Firefox. So that is, I think, the end of my story. I think I'm good on time. So I'd be happy to take questions. I'm happy to talk about Wasm core technology and standards, Wasm for security, or any application of Wasm that you're interested in. No stupid questions.
You talk about very lightweightness switching. Context switching is switching easy, but the examples you have, like sandboxing in Firefox, that's a highly collaborative workload, right? You're going to call the function anyway. You sort of know how much they cost. So essentially, you're just really isolating them. Is there a scenario where you will have a lot of like different applications that potentially someone malfunctioning? So I guess my question is more about, is there a need for some sort of a scheduler? How sophisticated does the scheduler need to be? Because in a real like kernel scheduler, it does all kind of, right? It will enforce certain kind of a resource isolation if the process does not go, it can be interrupted. So things like that. Like, is this a concern for Wasm as well?
I mean, so this is a really great question. This is an area that I'm actively working on and interested in. And it kind of gets into like, right, like how does user space thread scheduling work? How does concurrency work? So for sure, like, I mean, Wasm, the kind of like, the core mechanism is just like, gives you address spaces, it gives you isolation. And then you can put that into a context where you have concurrency, but that's like not part of the standard. Right, the way that like, you know, most folks do this today, right? Like Fastly or other folks, is right. They're running their Wasm runtime, and then like Tokyo is running underneath. I don't know if you're a Rust person, right? But like, you know, so they're using Tokyo underneath to like multiplex this thing, and Wasm has and the Wasm runtime will have its own preemption mechanism built in. There are performance challenges associated with that, which is something I'm actively working on, and I'm happy to talk about more. But yeah, does that kind of get at the question? Cool.
Hi, thank you for that talk. I wanted to ask about your thoughts on the recent Wasm runtime and what that might mean for multi-threaded applications of Wasm. For me in the past, that was a big blocker to usage and the year ago.
Oh, wait, sorry. So the question is about threading support?
Yeah, pretty much. And the newly released Wasm runtime which supports that.
This is the Wasmer stuff?
I don't think it's Wasm. I think it's released by Severcon. but yeah, essentially threading support and currency of that.
Well, so there's two aspects to threading support. One is like how do you do atomics and things like that, and so that's the Wasm thread standard, and it's like pretty far along. The other thing is like how do you create threads, and the challenge around that has been right that like there's a difference between like how do you do this in browsers and how do you do this on the host side. Browsers are like, well, we have web workers, right, and all of us who are like more focused on the non-web case, we're like, well, that's great for you, but we need some way to create threads. What's happened recently is there's this WASI threads proposal, which is out, and it's supported now in Wasm time, probably in some other places too. Whammer's had its own kind of like ad hoc support for threads for a while. There are things that I don't love about the WASI threads proposal because it's you actually create a new kind of instance per thread, but it really lit a fire under people's asses to like solve the problems we needed to solve to get the right threads proposal. And this has to do with kind of how browsers do threads and like saying, okay, like, because a Wasm context involves not just like, right, like the linear memory, but also certain tables. And you need to say, this is what I can safely share. This is what I cannot safely share. So the standard has to kind of like make its way along. So I would say, so threading support is like coming along. WASI threads is something you can use today. If you have like a use case where you need threads, like I think it's doable, but you're not totally unsupported, but you're also like not. I mean, this is the thing about the ecosystem, right? There's the parts where you're right on the path. There's the part where it's a little bit rocky, but like you will be fine. Like you will get the support you need if you're doing a real application. And there's like off in the weeds. Yeah.
Okay, thank you very much.
Yeah. All questions are good questions. So.
All examples were like Apple Silicon wasn't in any of the slides, so was there any specific differences or?
So, in terms of like the optimizations, or
the general idea, like was for simplicity, you put it all.
So ARM doesn't have like segmentation, so that's not something we can use. ARM v9 will have two forms of memory tagging. ARM v9 will have what's something called permission overlays, which is kind of like MPK, but a little bit better because it gives us XC permissions as well. So it's a very cool primitive. And it will also have something called memory tagging extensions, where we can tag things at like collections of byte granularity, so even finer granularity. So we think that we can use both of those to pull off this trick, but we haven't written the code in the paper yet. So, but yeah, there is no ARM v9 hardware out there except for, I think, in mobile phones right now. I think the new, like the 3rd generation Ampere stuff will have it, but I'm trying to get somebody at Ampere to give me one of those. So yeah, if you know anybody who has good connections at ARM or at Ampere who wants to give us some machines to build stuff for, that'd be great.
Thank you.
Is there?
Probably have another silly question.
Yeah, please.
Where to start? Like someone wants to start dipping toe, like and start working with Wasm. What would you suggest? Where to go? What to look?
I think the best supported tool chain. I mean, so I think that there's two tool chains that I think are really solid, and then the third one that we work on. That we use for Firefox, which actually is good for specific things. So Wasm time is super well supported and I think rock solid from a security standpoint. That's what Fastly builds on. That's what all the folks build on. So I would grab that. There's WASI Clang, right, for doing C and C++ stuff. Rust has really first-class support. So it depends on your language, right? So you need compiler support. You need something compile from, so compile whatever your code is to Wasm and then compile your Wasm to your local binary if you're AOTing, or you can do your JIT thing for whatever reason you want to do that. Once you've got those tools, I mean, I think just like, if you've got like, I think it's always good if you have like a need, right? You have a project, like something that is chewing on you that like, or that you're like, oh, okay, I need to solve this thing. But yeah, and so I mean, the community is really there's a like a bytecode alliance. I mean, like most of the communities on Zulip, kind of like you can ask core technology questions there. It's a very it's a pretty tight and pretty supportive community, kind of like the community around various programming languages. So yeah, if you have an application, I think you'll definitely find the support that you need around that. If you're interested in the secure sandboxing stuff, like sandboxing native code, you should talk to us.